Okay, finally we've made it to our last shape that we're going to talk about proofs with. So we know we're going to talk about the square, but first here, we're going to show in here, given the quadrilateral LMNP has the vertices given, prove it's a rhombus, but not a square. So we're getting pretty good at this point. We know what to do. -5, 10, 4, 3, 1, -8, and -8, -1. Okay, so just by looking at it, we probably can tell that it's not a square. And usually square ones are gonna, to prove it's a square, it needs the most properties, right? Not only would I need to prove it was a rhombus, but I'd have to show it had all rectangle properties too. So let's just start with what we know we want to prove it is. So we know the first thing we should be doing here is proving that it is in fact a rhombus. So our go-to way for that is just to show that all four sides are congruent. LM, if I do that distance formula, -5 subtract 4 squared, 10 subtract 3 squared. That's going to equal a -9 squared, which is 81, a 7 squared, which is 49. So we end up with the square root of 130. Okay, we repeat the process for each of the sides. So now I'm looking at MN. Notice I'm labeling each side as I go. So 4 subtract 1 squared plus 3 subtract -8 squared. So now we're looking at 3 squared, which is 9, 11 squared, which is 121, and we still get 130. So it's checking out so far. Again, though, we have to show it all four times if I want to prove that all four sides are congruent. So NP, we're going to look at 1 subtract a -8 squared plus -8 subtract a -1 squared. So 9 squared again is 81. -7 squared is going to get us positive 49. And we still end up with 130 under the radical. We have one last side to show. So when I'm doing that here, -5 subtract a -8 squared plus 10 subtract a -1 squared. We again end up with 9 plus 121. And we get 130. So right off the bat, the first thing I'm focusing on here is talking about that rhombus. So I can say all sides congruent. I show that with the distance formula. Therefore, LMNP is a rhombus. Okay, so it's the first thing I've shown. Because all four of those sides are congruent, we know it's a rhombus. Now here's the thing. A square has the most properties, so it's technically going to be the most work to prove. Because not only do you have to show it's a rhombus, you'd also have to show it was a rectangle as well. Now, clearly, this one's not going to have the rectangle properties that we want it to have. Because if we look, we can tell that there's no right angles. And that's a big part of the square. So we can easily show there's no right angles by looking at the slopes. So I'm going to look at LM. If I look at that slope here, I'm talking down 7 over 9. And if I look at the side next to it, MN, when I look at that slope, now I'm going up 11 over 3. Okay, just right there, I can stop. I can do all four sides if I want to. You'll see that the opposite sides are parallel because it's a rhombus, so it's got all the parallelogram properties. But right here, we see that consecutive sides not perpendicular, right? We didn't see the negative reciprocal slopes. Therefore, LM and P is not a square. Okay, so we just needed a reason why. Okay, now this is just one way of doing it, right? I could do it in a whole bunch of different ways. So I could have showed it was a rhombus by doing the four slopes and showing it's a parallelogram with the opposite sides parallel, and then looking at the slopes of the diagonals, because I know the diagonals have to be perpendicular. So I could have done that as well to show it was a rhombus, and then I would have already had my slopes, so I wouldn't have had to do any more math. I could have just explained why it can't be a square. So that's one way of doing it as well. Okay. Again, many different ways you could do these proofs. It's still a proof. So we know proofs are a lot of different ways to do it. It's whichever way we see it's going to work out best. So there's no real pressure with it. We just kind of do what we think is going to work the nicest for us. Okay. In the next one, we have a square ABCD, and we're given 3 of the 4 vertices, and we're trying to find the missing one. So first, if we look at A, it's at -8, -1. B is at 1, 4. And C is at -3, -10. So I have my 3 pieces. Now keep in mind, just in general, so I now have A, B, and D over here, right? They have to go in this circular pattern. That being said, because it has to follow a circular pattern around, that's why I know that C has to be somewhere in between B and D here. So we're going to try to find that exact location of it. So I can connect my sides AB and AD. And we're looking, so we can see that there's a perpendicular line. We could check with their slopes. So I'm going to start with that. I'm going to check with the slopes. My slope of AB okay, if I look at that, it's up 1, 2, 3, 4, 5 over 9. So up 5 over 9. And if I look at the slope of AD, we're looking down 9 over 5, which checks out because we said they were going to form a right angle. Okay, so AD and AB do in fact have a right angle in between them. So we know that these other 2 sides, one, opposite sides have to be parallel. So we know AB and DC have to have the same slope, same as AD and BC have to have the same slope. So I'm just going to count this slope. So if I go down here at D and I count the same slope up 5 over 9, something up 5 over 9, I get to that point right there. Well, let's check, see if it checks out. Okay, so if I look at that, if C is here, and then I can count up 5 over 9, which we just did, so we know that DC also has a slope of up 5 over 9. Let's verify that BC also had a slope of -9 over 5. So if I'm looking at that, down 9 over 5. Good. So we know we have the 4 right angles then. So that checks out. And I could do the distance formula to verify, but it didn't say I had to prove it. Because I counted the same amount, like I couldn't simplify in this case, but even if I could, if I don't simplify, then I know I'm maintaining those lengths. So I could have left it like that. I could draw on the diagonals and check them as well, but in this case, I'm good to go. So I know that C is at the coordinate 6, -5. Okay. That being said, we're going to see it in actual proof down here in, well, what should be 3. But what we're given is that the square ABCS is congruent to the square EFGS, and we're trying to prove that AS R is congruent to this piece here. Okay, so we see the word proof. We have no coordinates. We know it's a Euclidean style with our statement and our reason. Okay, the only thing I'm given is that square ABCS is congruent to square EFGS. Okay, so that's what I've been given. Okay, so right off the bat with proven triangles, we see one of our old familiar favorites, right? Automatically, SR is congruent to SR by the reflexive property. Now, don't overthink this one because we know it's a square, so that means we have a lot of properties to work with. So we already know that a square has 4 congruent sides. So I know, like, for ABCS, all 4 of these sides are congruent, but it's saying it's congruent to the other square as well. So I know all 4 of these sides are also congruent. So I already know all those sides are congruent without even having to do much more here. Now, there's only 2 sides that really affect our triangle. So I'm going to say AS is congruent to SE because squares have 4 congruent sides. And congruent squares have all sides congruent. Okay, so if we have 2 squares that are congruent to each other, we already knew that the square itself had 4 congruent sides, but if I know it's congruent to another square, that means all those square sides have to be congruent to one another. Okay, so I already have 2 checks already. So that was my second check, right? I already had the reflexive as the first. We normally need 3 to get the triangles. So this one's going to take an extra step in here. When I start this, I also know that squares have 4 congruent right angles. So in here, I'm going to start with the 2 that I care about. The 2 that are closest to helping us are here 1 and 2. Okay, and I can say in that reason, angle 1 congruent to angle 2. Squares have congruent right angles. Okay, so we don't have to do anything fancy there because if we know it's a right angle, 90 degrees is 90 degrees no matter where it is. So I don't even have to worry about having 2 separate triangles or squares that have it. But the next part, now this is a little bit of a throwback for us. We have to know that these 2 angles and these 2 angles, they're on a straight line. So we know that angles 3 and 4, they're supplementary because they're angles on a line. And remember, there was a rule that we used back before. So I'm going to jump and say that angle 3 is congruent to angle 4 because supplements of congruent angles are congruent. Okay, so those, we know that 3 and 4 would have to be supplementary to 1 and 2 respectively because they're angles on a line. So any angle on a line adds up to 180. We also know that they're both 90. Okay, so in here, we know that they're both 90 degrees. And then if I look at my reasoning, if I knew 1 and 2 were 90, I know that 3 and 4 are both 90 degrees. So when I say that the triangle ASR is congruent to the triangle ESR, if we look at our method closely, I'm going to say HL, because if I look at this, 1, we made that right angle in here, so 3 has to be a right angle because it's a supplement to a 90 degree. We had this side and this side, so that spells out angle side, which we never want to do, but we can fix that by using HL because we do in fact have a right angle. 3 and 4 have to be right angle because supplements of right angles have to be 90 degrees as well. Okay. So that would be our proof there. Then we just have some questions about squares in general. So if we had a square that had a side length of 6, that means all 4 of these sides are 6, which would be its diagonal. So if I'm looking at the diagonal here, it's like we were drawing a diagonal, and we could pull out a right triangle. And then it's a quick one, right? 6 squared plus 6 squared equals x squared. 36 plus 36 equals x squared. And you could plug it into your calculator, see which one matches. This would break up to 36 and 2. So we'd be looking at choice 3 there. In the next one, the diagonals of a square ABCD intersect at point E. If we're given BE is equal to 10, which of the following is AB? So it doesn't matter how we label A, B, C, D. We know that AC and BD intersect at this point E. And we know that BE here is 10. If we want to know the length of AB, well, we know that the diagonals bisect, and we know the diagonals are congruent, so we know all these pieces around have to be 10. Okay, we also know that the diagonals are, in fact, perpendicular. So, same idea again. 10 squared plus 10 squared equals x squared. We end up with 200 because we get 100 plus 100. Take the square root of both sides. So we get 10 radical 2 there. Okay. So this last one's a challenge question. You don't have to do it, but if you want to give it a try, we'll do it tomorrow in class or next time we see each other. So if you want to do this one, try it. If not, no worries, but this one is going to be a little bit of a challenge. I want to see how you guys get there. Okay. All right, guys. Thanks for watching.